All right, so let me close some of these extra windows. All right, so here's a few news articles that are kind of fun. So Boston Dynamics has this dog called Spot, and now two police agencies have begun actually using it on cases. There's no real details yet, but some people regard these robots as terrifying, but anyway, they can open doors and so on. And a whole bunch of them are strong enough to pull a truck and so on. So I'm not quite sure what they're going to do with them, but robots are increasingly used by police and other things these days. This is pretty entertaining. The Trump supporters are making pictures of him on bodybuilders' bodies to indicate their feeling that he is a heroic fellow. So that's entertaining stuff. And this is the big issue of censoring social media. This is one rather like what Alexandra Ocasio-Cortez asked Zuckerberg about. So people that don't like Elizabeth Warren made a fake site pretending to be a supporter of her, and then posted a picture of her, a picture of someone black supporting her, which is fake, with the idea that people would figure out it was fake and blame Elizabeth Warren for it. So that's a little bit subtle. And of course, they're upset that they were unable to stop Twitter from spreading it. And Twitter said this didn't violate their terms of service. And it's definitely an interesting edge case. I remember Mad Magazine from my childhood when they decided that it is perfectly legal to make satires on politicians. And I think as far as the law goes, they're going to have a hard time taking it down. But of course, Twitter could define any standards they want for the media on their platform, but they decided not to take that down. So anyway, I was very surprised to see this. Trump actually wants to support the pro-democracy protesters in Hong Kong, or to be fair, he was forced into this. The vote for it was unanimous in the Senate, and only one person voted against it in the House. So Trump had to either sign it or face what would probably be a veto overthrow. But anyway, he's always very ambivalent about whether he supports the Hong Kong people or mainland China here, like he doesn't want to get involved. But the rest of the US government strongly wants to support the protesters in Hong Kong, although it's not clear what they're actually going to do about it, but at least they're saying friendly things. So that may give them some comfort. A lot of news about this for the last decade anyway. Rich people don't have babies as much. So birth rates falling in the US, also in Japan and many other nations. Economists are freaking out, saying this means that there won't be enough young people working to support all the old people that need money. But certainly on a larger scale, you definitely want less humans in the world, have less pollution and so on. So we'll see how it goes. Anyway, I'm reading about this a lot. The younger generation is having less sex, getting married less, having kids less. And I think it's a real trend. And it's nothing new. Same thing happened in ancient Rome and many other societies. Once people get rich enough, then they largely decide not to bother having families. This was pretty interesting. For more than 10 years, UPS employees as an insider job have been shipping around vast amounts of drugs because they have prevention measures inside UPS to catch this stuff, but the employees know how to go around them. So they put false addresses on the package and had a secret way of telling which ones were this way and carefully sent them to some other address, bypassing all the controls. And the law enforcement people say that UPS did not cooperate with them and would not help them catch them. And that's why they kept on going for 10 years before they were able to finally get enough evidence to arrest them. UPS claims they're cooperating. You know, all the details aren't out yet, but anyway, this is a issue at companies. They say the biggest threat is the insider threat. Anyway, there's Docker, and apparently, I've got a couple projects where people use Docker, but I haven't looked into it much. Apparently, there are Docker admin ports listening on network ports. I don't think that's true of my servers running Docker, but anyway, it might be. If so, I haven't noticed it any more than these people have. Apparently, under some circumstances, you install Docker, and you will then see there's a listening port that gives you administrative privileges over it. So they're able to take over your Docker. And what they're doing is installing Alpine Linux and executing a payload to mine cryptocurrency. Alpine Linux is bloody awesome. I learned about it from CTF. It's one of the super small Linuxes. For like 30 megabytes, you can have a running version of Linux. So if you just want a small, fast container, it's the thing to use. Anyway, that's interesting. And I wonder if I can reproduce that exploit and make it into a project. That would be fun. HewlettPackard has a mind-blowing flaw. They don't explain why, but this is very suspicious. 32768 is the largest 16-bit signed integer. So this does look like a simple integer overflow, but what happens is on this hour, if you read an HP SSD, it self-destructs, losing all your data permanently with no warning. So that's pretty impressive. And they give a list of models to check. That seems like a very severe flaw. You lose all your data. Anyway, and I don't know how you're supposed to tell, but they do give you a list of model numbers and such, so that might be some use. Let's see what else we got. Might be good. This is, I heard a lot about this one. And there's a few others. So China claims they're going to do something about IP. Of course, they've said this for years, that they're going to stop pirating, and then they just continue to pirate and just lie about it. But now they're claiming again that they could reform their intellectual property laws to stop stealing so much intellectual property, and maybe that would make it easier to be a good trading partner. We'll see what happens. Their history has been very clear that they will just deny that they're doing it and just do it right in front of you and not even hide it or anything. I've been reading a book talking about this. Putin started this, where you just change your story every day. You just lie openly. In the past, the Russians and other people make a big deal and try to make lies plausible. But this modern trend, which Trump exemplifies, is to just lie constantly, don't even bother to have any excuse for it, and just expect people to forget that the truth exists. It's an interesting new technique that's quite effective. And I think China had it first, really. Anyway, so Uber, it got kicked out of London. Well, they can drive now, but they've tried before. Uber is in big trouble. They had a huge valuation, but now they're below zero, losing money. It looks like Uber and Lyft are both dropping like a stone. And there's a big argument that the whole unicorn movement of Silicon Valley is going down. All these people thought they could make a pile of money by disrupting an existing business, by just having an internet version like Airbnb that would just blast into a market that was already there, like loaning apartments, and do it a different way and cut out the middleman and cut out the government regulations. And in general, that didn't turn out to be as brilliant as everybody thought. And I think WeWork was the big disaster. Evaluated as $49 billion and it sunk down to $7 billion. Everybody lost a lot of money, except for the CEO that got paid more than $1.5 billion just to preside over this failure. So, by the way, that's the same thing happening at the college. The chancellor wants to get another $500,000 pay, and he just announced today that after canceling 200 classes last week, he's going to cancel another 200 next week, because his budget plan involved taking all the money from federal grants and just putting it in the coffers. And he just realized, like Monday, that's not legal. You can't do that, which any of us could have told him. So now he's going to have another round of cuts. So we thought we had escaped it, and I thought I would be able to teach the advanced security classes next semester, but right now nobody knows anything. There was a meeting scheduled today to explain it to us, and they canceled the meeting because it's all in the air again. So I think the most likely consequence is next week they will indeed fire all the part-timers next semester. They will certainly cancel a whole bunch of classes that students have already enrolled into. And I wouldn't be surprised if they have yet a third round of cuts after this, because I think he has a couple other fishy measures. However, I should be fair. I'm picking on the administration here. They are no different than the administration in Washington. This is something every Republican administration has done for my entire life, is cut taxes and then pretend money is going to come from nowhere. And what the chancellor has done repeatedly here is pretend money is going to come from nowhere and not bother cutting things enough. And so he's just continuing in the same vein. It's not any worse than what happens in Washington, but it's not any better. What's that? He wanted to take federal grants that we have and just put it in the general fund to pump it up. And of course, when you get money from a grant, it's earmarked for a certain purpose. You're not allowed to just grab it and put it in a general fund. And he pretended he could do that. So, what's that?
So he can take the money?
Well, no, he can't. He can't take the money. What did you say? Oh, there are. Yeah, I think they have to like pass laws for it or something. I know there's certain conditions under which you can do it, but he doesn't have that power.
Congress did, the city
Well, Congress.
supervisor did it too.
Yeah, Congress has the power, and probably the supervisor of a city have a power, but an institution that gets a grant is not allowed to just suddenly decide to ignore the grant provision and reallocate that money somewhere else. So Google had protesters that are complaining about the entire thing. Google's had a lot of whistleblowers leaking out their military contracts and such, and now they're firing them, claiming that they were investigating other people's schedules to plan these rallies and sending internal messages to bring people to these protest rallies, and that violated their privacy. So anyway, they were leaking out internal Google data or abusing internal Google data. Anyway, so I think that's enough of the news. What I want to show you tonight, I was going to show you the Hopper debugger, but I really don't think that makes any sense anymore because I think Ghidra completely replaces the Hopper debugger. And I may talk about that next week or a future week, but what I want to show you now is what I have been doing, which is ARM. And I made 3 new projects out here today. So that's all I want to show you because ARM is very important. Let me bring this stuff up and talk about it. So the point of ARM is that it is a reduced instruction set. This was the original difference between Apples and PCs. Apples used Motorola RISC computing. There are 2 general philosophies in computing when you design processors. One is you make the Intel technique is CISC, complex instruction set computing. There are something like 10,000 machine language instructions in the Intel processor. There's a pretty dull list. There's like move register to register, move immediate value to register, move immediate value to memory, move memory plus immediate value address back to register. You know, there's like 100 different kinds of move. And so you have many, many complicated instructions. And therefore, those instructions are optimized in the hardware. So if you had a compiler and you had a high-level language program doing something like a loop or a mathematical calculation, it could in principle run faster if it used complex machine language instructions to use less total instructions to accomplish the job. But in fact, what happens is most people who write compilers don't really pay attention to all these complicated instructions, and they show that like 80 or 90% of them are in fact never used by compiled code. The compiler just uses simple instructions from before. So an alternative way to go, which is what Motorola did, and the early Apples, was reduced instruction set, where you have a small number of instructions in the processor, highly optimized, and now when you compile code, it turns into more total machine language instructions, but they thought it would be faster under some circumstances. And ARM is the latest generation of reduced instruction set computing. The individual assembly language instructions do much less. And it turns out to be very effective. The studies have shown that you can do much more computing for less power, which means less heat dissipation or less battery consumption. So phones run ARM, and mobile devices, Internet of Things devices run ARM. And I've read articles in the last couple of years saying all computers are going to switch to ARM very soon. It will save so much money. Servers are going to run on ARM, and desktop machines are going to run on ARM, although none of that seems to happen yet. Anyway, so if you want to exploit Internet of Things devices like routers or other things like that, you got to learn how to exploit ARM. So I put in some ARM projects. And the first thing is to use this thing called QEMU, and you can emulate ARM. Now, I showed you last week how to put in FreeDOS, I think here. So you can run this, you install this thing called QEMU, which is like a virtual machine, but it is in fact an emulator. It is emulating hardware, so you can run a different kind of hardware on your operating system. So you can run FreeDOS on Intel. This is a Google Cloud server running on an Intel processor, and you can run DOS in it. which is not a virtual machine, it's emulated. It's QEMU simulating an i386, a 32-bit processor on top of the underlying 64-bit processor. And here is DOS running it. This is free DOS, of course, because I don't have license for Microsoft DOS. Yeah, here's a question. Speaking of RISC, do any devices still use MIPS? It's a good question, and I don't really know the answer. I do know they teach MIPS here. I think something still runs MIPS, but I'm not sure what it might be. It's a good question. By the way, you can totally emulate MIPS with QEMU. Yeah.
It's pretty popular in China.
Popular in science.
In China.
In China. Oh, okay. Well, what's it running on? Routers or what?
Actually, the supercomputer is inside the core.
There's supercomputers running on MIPS?
The core is.
The core is MIPS? Oh, well, maybe it's got its virtues then. It's a very good question. I don't know much about MIPS. I know they teach it here. And so somebody must use it, but I'm not aware of any common device that's running on MIPS in America. Yeah, well, maybe it's good. Great. The assembly class teaches MIPS. Yeah, I know. I've heard that they teach MIPS for some reason. Anyway, but once you learn one assembly, the others are comparable, but these are good points. Anyway, so this is FreeDOS running, and then I got Alpine Linux, which we just heard about in the news. People are running ransomware on containers in Alpine Linux for the same reason why I think it's awesome. You can have a really small Linux system. It's easy to download, easy to run, and all that jazz. So I went to Alpine Linux and downloaded it. There are a bunch of boot systems around here. Here's a special one made for virtual machines, so you can get the 64 or 32-bit version. I downloaded the 32-bit version. And then it's a little bit of a hassle to make it. You have to use this QEMU system to first create a hard disk. And there's something called QCOW format. I don't know what that stands for, but the format for the hard drives is QCOW2. So you make a 512 megabyte hard drive, which is pretty small. That's the point of this. And then you can boot from the virtual CD, the ISO file, and then you can do an installation. And it's a standard non-graphical Linux installation, which means it has about 20 questions to answer, which can get sort of confusing. But anyway, after you do all that junk, you will have glorious Alpine Linux running in a virtual machine on your graphical desktop on a Debian Linux substrate underneath it. And of course, all these run pretty slowly. The emulator is not as fast as virtualization. Modern virtualization is not emulating the hardware. What it's doing is actually passing the individual assembly language down to the processor through the virtualization substrate using the hardware-assisted virtualization like VTX to make it really fast. This is the opposite. It's simulating a different processor in software. So of course, every instruction in the simulated OS involves a lot of instructions to translate that down. So it's going to run a lot slower than native installations. It's better if you want to experiment with a lot of different hardware without having to buy a lot of hardware, which is my interest. But the penalty is, of course, it runs much slower. All right, so let's take a look at Raspbian, which is ARM, which was quite a big deal. And I put it in a separate project because it took quite a while to figure out how to do it. It turns out to be a much bigger image, and there are some strange limitations. So here's Raspbian in QEMU. And what I did here was I switched to non-graphical mode, which was the only way I could make it small enough. Before this, it ran really slowly and really irritated me, and I've learned how to do it with no graphics. So what you do is you just download, you get GDown, so you can download directly from a Google Drive. And then you download this thing from a Google Drive, which is an image that somebody else put up. A guy made a bunch of QEMU images and put them up in the drive. So you get this thing, and when you unzip it, it's about 5 gigs big. And you'll have a script here. Let me just bring it up live. I've got my Google images here, and here we are. It's already running. I'm going to leave it with Control-C. Okay. So here I am in my operating system. If I go to the home directory, you'll see I have the original file here, which is armvstretch.zip. That is 1.5 gigs. When you unzip it, it turns into some larger amount like 5 gigs. It turns out you can still run this on a default Debian Linux cloud server if you have nothing else on it. So as you just make a new one, it'll have a 10 gig hard disk. You don't need any more processor than whatever the minimum is, or any more disk than what the minimum is, as long as you're not trying to run anything else on this machine. So you can unzip this thing. It'll create this folder called armv6 stretch, and it's called that because it emulates Raspberry Pi hardware, which is ARM version 6, and then it runs Debian Stretch Linux on top of it. So if you go in here, it's kind of twisted what we've got. You will find in here some start scripts. You can run it on Windows with the start.bat, and you can run it on Linux with the start.sh. And if you look at the Linux scripts, you'll see how it works. All this is doing is running this system ARM. Let me get my window to fit on there. It's just running QEMU. This is just a long command. So here's the CPU, ARM 1176, some version of ARM. Here, 256 megs of RAM, not very much at all. And it's got a couple of extra ports, 6987 mapped to 4444 and 5022 mapped to 22. So your virtual machine can connect to the internet on those ports. And we could have other commands here to connect other ports, but that's enough for everything we're doing here. Then here's the kernel QEMU, which had to be included, and other settings here, but that's the main thing. So it's going to run this thing called Raspbian Stretch.img. That's the virtual hard drive. I think it is 6987 that goes outside, and it's 4444 inside. But we'll see. I will use it in a little while. It's easy to get them confused. So you start this thing, and here it boots up. You'll see all the boot up messages, and you'll see a Raspberry, welcome to Raspbian there. This is booting without opening another graphical window, which makes it much smaller and much faster. There is one very annoying thing about this. You can't press Control-C in the Raspberry Pi, which is a command you use a lot. If you hit Control-C, it will quit and kill the whole emulator and go back to the Debian underneath. There is some way to prevent that, but I haven't figured out how yet. So I keep on accidentally getting kicked out because I hit Control-C a lot for various reasons, and you have to never hit Control-C when you're using this thing. Anyway, there is supposedly some way to prevent that, but I haven't gotten there yet. So notice it has this typical emulated IP address of 10.02.15. That's the same address you'll get with a VirtualBox machine. So it is behind a router, which would mean you couldn't have any listening ports, and that's why they mapped 2 of those ports out, as you saw. 22 and 4444 map out. So those are the only ports you can use for listening processes in this configuration. Yeah?
This one doesn't like the Control-C?
Yes. If you hit Control-C here, you will quit being in Raspberry entirely and go back down to the Google Cloud Debian. Okay. Instead of just doing things like showing you what line you're on in Nano or others, or canceling your current command. And I've become aware of how often I hit Control-C. I frequently find I'm out of the OS and I have to restart it again. So and when you log in, the username is Pi and the password is Raspberry. All right, so now that I'm in, it is slow. It will take a while before I get my prompt. Okay, now I'm in. So if I look at my working directory, I'm in Home Pi. And if I do ls, I got a bunch of files I've created here for various projects. If you go to the root of the system, you'll see just a standard Linux file system. The Raspberry Pi Raspbian is very much like just Ubuntu Linux or Debian Linux. It's not terribly different. The only big difference is it runs on ARM, and we're going to see how much difference that makes. So once you're in here, you can make this program pwd.c, which is the same vulnerable program we've used before. So pwd.c, you've seen this thing before. It has a main routine that calls a subroutine called testpw, and then it prints either fail or calls win. It will in fact always return 1 and always print fail. It will never go to win, and your goal is to run this win routine, even though no possible password will do that. And the way you can do it, of course, is there's only room for 10 characters, but it reads up to 50 characters from you. So by doing a buffer overflow, you can redirect execution down to that win command. Now, what we've done in the past is use GDB to debug this. In this case, GDB is very buggy. If you run GDB natively on the Raspbian, it crashes all the time and fails in irritating mode. irritating ways. And I tried to update it, and that turned out to be essentially impossible. But I found we can go to what you really should do. You should not be running a debugger on an Internet of Things device. They're always too small and too weak. You're not supposed to do it that way. The way you debug it is by running GDB server on the device, which is a small stub which debugs it and sends all the information to a network socket, and then you run the debugger on another machine. And that's what we're going to do here, which is the correct procedure for small devices. So anyway, let's compile this thing the same old way, except I use -G to get symbols so we can do source level debugging, which we've done before. So it's GDB. I can use copy and paste. So if I compile it, all right, that will compile it. And you notice it takes maybe 5 seconds because it is an emulator, it runs very slow. Then I can run it and ask me for a password. If I put in hello, it says fail. If I run it again, and then I put in a long password, I get a segmentation fault. So far, it looks just like anything else. Of course, the functionality of the program will be exactly the same. That's the whole point of the compiler. The C source code is exactly the same. So the logical steps are the same, but the underlying hardware and software is different. So we've seen a crash. So now here's how you debug it. Use GDB server, and multi means you can run it multiple times, although in fact that doesn't work very well. And then you choose a port. And like I say, we observed that 4444 maps to 6987 or something. So we have to use port 4444 inside the Raspberry to listen. So I start this listening. Now it's listening on port 4444, and now I connect from another machine. And I have another machine here. So this is my Debian 5 machine. This is just a default Debian machine. So I'm going to bring back my other one there so you can kind of see them both. And for the moment, I'll readjust these sizes. Not much is going to happen in this one, so I'll just put it up there. This is where most of the action is going to be. Okay, now I run. Now, if I ran GDB, I would be running an Intel 64-based debugger, which is not going to be able to debug ARM code. So I have to install, I create another Debian cloud server, and you do all this junk to install a different ARM-based version of GDB. And so you download this thing from Linaro, has this project, and you unzip it, and you end up taking this. This is the full name of this thing, ARM Linux GNU ABAIHF, whatever the heck that means. I just called it ARM GDB. So after you've downloaded this thing and unzipped it, now you can run ARM GDB. So let me get this. This is the all-important command. Okay, so I go here and I run ARM. I put it right here, ARM GDB, because it's like 6 folders down with ridiculously long names. So after unzipping it and finding it, I just put it here. So now it is running the Linaro GDB. And if you run this, here, then you can connect remotely. So this will connect. This is the IP address of my QEMU emulated ARM. And this, of course, is the external port. We saw that an inside port of 4444 turns into an external port of 6987. So this will connect to the remote server, and you see it up here, remote debugging from that host. Now, there are some problems. It doesn't have access to the symbols because the symbols are in the code that's on the other machine. There are various ways to solve this. In this case, we're lucky because this debugger actually supports remote gets. So I can get the source code and the compiled code from the ARM machine and move it onto my Debian machine. But I have to put it in the right window. There we are. That will get it, and that will get it. So now I have a local copy on the x64 Debian of some ARM code which cannot run there. But the ARM-based debugger can read it to find the symbols. So now that I've done that, I have to tell it to use the local file called pwd to get the symbols. So that's what this does. Now it's reading symbols from this location on my Debian server running on x64 and finding the symbols. So now that it's done that, I can now do break main. I couldn't do this before because it wouldn't know where main was. But now I can put a breakpoint in main and I can run. And this will start the program. And let me put this one higher for the convenience of people in the room and move this down low because not much is happening down there. All right. And so this is now ready. And it looks like I forgot, it couldn't run it because I forgot to specify the remote exec file. So I skipped a step, which is this one. You have to tell it what file to run. Although later on, we're going to avoid this step. But in this case, we have to set it here. Now I should be able to run. Okay, and it's run to the breakpoint. And this is where the program started. Now I can also list the source code because remember we allowed source code symbols. So here's the source code for this program. And this is the first statement in main, if I continue, is if test PW. So this is what happens when you put a break at main. The first line of main had a breakpoint. Nothing has happened yet. It's just loaded it up and it's ready to go. So now I can put a breakpoint where we're going to need it. Let me go back to my list. Remember, the buffer overflow is right here. So if you want to understand it, you have to break here on line 9, which is after it's read a password from the user and before it's tried to return and it's going to crash. So we want to break at line 9. So that's all you have to do, break 9. Now you can continue and proceed to 9. And now it's hit the breakpoint and it's asking me for the password down here. So now I put in, say, AAAA, a short password that's not going to overflow in the Raspberry. And now I go back to the Debian and I can now examine things. If you do info registers, for example, the same thing we did almost all the time, you get to see the glorious ARM registers. Everything is called R, and R is always 32 bits long here. In 64-bit ARM, which is what I tried first, R is 64 bits and X is the lower 32 bits of them, but 64-bit ARM turned out to be very, very, very difficult to deal with. 32-bit is hard enough, so I went back to that. So here's the registers up to R12, then there's stack pointer and the program counter down here. So this is the stack pointer pointing to this address BEFF and so on. Here's the program counter pointing to a really low address, 10,500. So I can examine the stack the same way we'd usually do it, say 20x SP. It's not ESP, it's just SP. So here's the stack. And I'm not seeing what I expected to see on there, so I'm getting confused. Let me check. I expected to see the AAAA on there. Let me see if I can figure out what happened here. Let's see where I am in the breakpoints. It hit a breakpoint here in password line 9. Okay, it made it to the breakpoint. And here it read AAA, but somehow I'm not seeing it up there. That's pretty annoying. Let's just try continuing. Okay, now it segfaulted, which really doesn't make any sense. All right, let me, when you foul it all up, which happens to me a lot, if you try to close this with Control-C, it will kill the Raspberry Pi completely and force you to restart it. The polite way to get out is monitor, exit. That will close the GDB server down here. Now I can quit this one with Q and Y, and now I can do it all over again. Let me see if I can get it right. I do GDB server here. Okay, now I run GDB up here. ARM GDB. Now I have to do this junk. I have to do target extended. I don't need to do the remote get again because I've already done that and it's still stored in the local file system. But I do need to tell it the file and set the remote exec file. Okay. Now I should be able to break main and run. Let's see if that works. Okay. And now I've made it to the start of the program. Now I can continue. And it's asking for the password, AAAA. And now it exited. We have printed, fail, and exited. So my breakpoint is totally failing. Oh, I forgot to set the breakpoint. Well, that'll do it. Okay, fine. All right, so I do monitor. Now, by the way, when we're doing it locally, we would just run the program again. If you try that here, it will really not work. You will, in fact, see old memory contents here that no longer reflect the situation down there. That gave me a headache for a while until I learned to always just leave everything and come back. Otherwise, you will get weird stuff, which will not help. So I exit here and I quit here. Now I'm totally out. Now I start it again. Now I run the arm thing again. Now I set my target. So that makes the connection. Now I set the file, set the break and run. Okay, that gets me to here. Now I have to break 9. Now I continue. Now it's going to ask for the password. And now it hits the breakpoint. This looks better. Now if I do x20x, stack pointer, there we are. Now things look good. Now I see 41, 41, 41, 41. That is the A's I put in, and there's no overflow yet. So this is the stack pointer. One thing that is manifestly missing in ARM is EBP. There is registers that sometimes serve this purpose. There are weird complexities. It's not as simple as knowing quite where the base of the stack is. But I can find the stored instruction pointer another way. Notice this number here, 10544. That is in fact the stored instruction pointer, and I can verify it this way by doing a disassemble of main. And when I do, here's another irritation. Here I call test PW. BL is branch with link. B is a branch, that's a jump from which you cannot return. BL is what passes for call, where you branch and you save a return address, which is the link to come back. So this is going to branch and call test PW, and this is the next instruction, and that number should look familiar. It's 10544. So that is the stored instruction pointer. It's there, just 16 bytes down the stack from my A's. One thing I'll just mention in passing is down here you have a BL to just a meaningless number, and here's another BL. This is like a printf or scanf. I don't have the right labels for C libraries. So my C library calls are not going to give me the names here. Now there is some way to overcome that. There is some way to download the addresses for C library and put them on Linux and link to them inside GDB to fix that, but I ran out of strength. I didn't get that working because we don't really need it. But still, it would be nice to get that working. Anyway, so now if I look at the stack again, I can see here's the A's and there's the 10544, which is the return address. So obviously, if I put in 1, 2, 3, 4 groups of 4 letters, the 5th group of 4 letters will hit this. So I can do that one. Now I'm just going to make my life easier by just leaving and coming back every time. So I'm going to quit here. Okay. And I'm going to try something else that's not in the instructions, but it turned out to be pretty fun. You can put it here. You can put the name of the executable there, and then you don't have to set remote executable. All right, so now I run this one. That saves me at least one step. Now I just have to give it the IP address of the thing I want to remotely debug. I wonder if I ever started the recording. Good, okay, anyway. And now that I've done that, the only thing I need to do is set the local file, and then I should be able to debug. All right, and it gives me some nonsense, I just ignore it. Now I should be able to break 9. Now I should be able to run to the breakpoint, continue. Perhaps I need to do run. Yeah. Oops, already did. I want to start it again. Now I do continue. And I hit this. Okay, now I'm going to put in AAAA. Okay. Now I hit the breakpoint. Now I should be able to examine the stack. And you see, here's the A's, and there's the stored stack pointer. So now I've been able to corrupt it with EEEE. So if I continue now, it's going to crash with EEEEO. It looks like I'm off by 1 character, but that's the point. So some of the characters I typed in control the stack pointer. So I can now win the game. First, I have to get out of here with monitor, exit, and then get out of here, and then run this again, and then run this again, and then connect again, which is this one, and then this one. So I get the symbols, and I don't know why it keeps telling me I'm restarting things, but when you say yes all the time, it seems to work. And now I can put a break, Now I've got the thing loaded. I can run it and it will break at the start. Oh, I've read some. All right. Now I can do disassemble main, and you'll see the assembly code for main, and I can do disassemble win. Win is the function I want to hit. So now I have the address I want to feed in. So 10, that's the address I need, 1051C. If I can redirect execution to there, I can win the game. So now I have all the information I need to make a Python exploit. And I think I'll just design it in a text editor here. So its prefix is A, B, C, D. All right, let's make that a little bigger. And now the EIP is going to be this address backwards, which is 1C050100. There, and so it's print pre plus EIP. That should be all I need to win the game. So that's the Python code I want to run. Now I could perhaps find some way to do it over the network, but why bother? I'm just going to run it locally on the Raspberry Pi. So I'm going to monitor, exit here, and then quit here, and then go down to the Raspberry Pi. And so I'm going to nano, let me move this up to make it easier. So nano, demo 1, I don't care what I call it. Okay. It's kind of slow and kind of buggy. There are graphical mistakes here, but anyway, there's the code I've copied. Okay, save that. And to test it, I'm going to run it, Python demo. Demo 1, it's not, there, it worked. It printed something, but it didn't scroll right. Now, because I used nano, it fouled up the scroll. One solution is clear, another one is to resize the window. Nano, of course, fouls up. Anything using graphics much tends to foul up in this limited environment. But there it is, A, B, C, D, and then some unprintable stuff. So it's probably all right. So what I'm going to do is, as usual, I'm going to put that in a file. I'll call it foo. All right. And now I can run the server based on that. And I want to see it in the debugger first. So I'm going to run this, and I want password to get its data from foo. This is an easy way to do that. So it will run that command and pipe it over the network. So that is my network debugging in GDB server. And here is my other end of it. So I start ARM. Now I need to do this again to connect, and the local file from which it will get symbols, and yes. And now I just want to run. I'm not going to have to type in a password or anything. I'm going to need to do, I think, continue, because it automatically breaks at the start or something there. And now I win. See, you win appears down here. So I made it. Now, if I want to see why I win, I can exit with monitor, exit, and then I can restart it here. I'm going to quit this entirely before I get confused. Okay, run this. Now I run this. Now I have to connect to my target and specify the file. And now break 9 and run and continue, because that's the start breakpoint. Here's the breakpoint after the overflow. I didn't have to type in anything because it knows already, but I should be able to examine the stack. Okay, and so here's the ABCD, there's the address 1051C, and if I disassemble win, it is indeed 1051C. So if I continue, it will go through that and print out you win. So that's good. Now, if you want to be complete, I can monitor exit, and I can quit up here, and I can run it directly here. And there's something else worth mentioning, by the way. If I just run this program, pwd, and I put in an A and it ends, and then I just run it again and put in an A and it ends. Notice I printed out a pointer here deliberately. Oh, and it looks like the pointer is changing. When I did this before, there didn't seem to be any address space layout randomization, but now there does, which would make me think that this exploit is not going to work. But I think it doesn't randomize the text section. I'm not sure, because I think the exploit does work. Let's try it. So I just run this from foo, and I win. And I should not be winning if address space layout randomization was doing any good, but apparently ASLR affects only the stack and not the text section. So anyway, that's so it works outside the debugger and inside the debugger. And I'm planning to get up to doing trampoline attacks and return-oriented programming attacks here, but there are serious problems on the way there, and I'm only about halfway there here. So that, I think, is all there is in the first one, where you do the very simple buffer overflow in ARM. And the next one, I have to warn you, is incomplete. I've been trying to get shellcode injected on ARM, and I was horrified to discover that my Metasploit cannot generate ARM code, as far as I can tell, which is surprising. Yeah.
Maybe the pro version does, but not the free version.
It could be. I found some weird Python-based hacking library that claims it can generate ARM shellcode, and I think I'm going to have to figure it out, because all my other attempts to make ARM shellcode have kind of crashed and burned. But anyway, I got partway there with this next project, and I figured I'd give it to you in its current weakened form. This stuff will get better. So here's as far as I got with shellcode. And I found tutorials that talk about this, but they don't really take you all the way. Is ARM always little endian? I think it is, but I'm not sure. Anyway, so we have this thing all set up with the same thing. Now we make password 2. The idea was to just make this program a little better. So let me make this, I'll just cat, PW, and move it up so you can see it. PWD2. C, is it C? I think it is C. There we go. All I did here was get rid of the win, because I don't care, and make it 800. So it reads 800 characters from standard in. So you can just put in an exploit code. That was my plan. So it's exactly the same otherwise. You read a password into a place that only reserves room for 10, but you can put in up to 800 bytes. So I should be able to put in code. That was the plan. Things went awry. Anyway, so once you've done that, you can compile this thing and have, after you compile it, you get PWD2. And if you put in AA, you are all done. And if you put in something longer, then you get a seg fault. So it's exactly the same thing as before. But the seg fault means you control the EIP, and you can then jump into some of the stuff you've injected and execute it. And I was able to get some proof of concepts of that working. So here, you can run it to debug PWD2. So let me get that going. Let's get this thing listening. Okay, now it's listening. And not much is going to happen here, so I'll shove that down to the bottom. This is where the action's going to be. So I go here, and I connect with exactly the same command, because I specified the name of the executable at the other end. Now, the first time, I need to get a copy of the C code and the executable, although I think the only thing I actually need is the executable, and then specify to use that file to look up symbols. So I'm here, and it keeps asking me these questions, and I just keep saying, yes, it seems to work. Then I can break main, and then continue, or is it start? It's run. Okay, now I'm running, and now I can list the source code, which will be the same thing we saw before. And again, just like before, line 8 is where the buffer overflow is. So line 9 is where I want to put a breakpoint. All right, and now I can disassemble the main, and we can take a look at the main code, which is going to turn out to be pretty useful. Main, okay. So this, oh, by the way, if you want to see the raw bytes, it's disassemble/R, which is pretty handy. Okay, so now this is the code. And here is the branch to test PW. Then it comes back and loads a register, taking the program counter adding 8 to it, and taking the data in that address and putting it in register 0. That's what this is. This is how indirect looks like. Here's another kind of indirect down here, by the way. These are 2 ways to refer to the same thing. I don't know why they make it 2 ways. Here it's inside the brackets, and there it's outside the brackets. And it turns out, for good, clean fun, that only some of them are valid for some instructions, and only the other ones are valid for other instructions. So it can be pretty annoying. Anyway, yeah.
What's the difference between the /r and those?
Without the /r, you don't get this. You don't get to see the raw binaries. All you see is the instructions. And the reason I put it here is because of one of the big differences between ARM and Intel. In Intel, the instructions are all different lengths. Remember, CC and 90 are single bytes and other things are long. In ARM, everything is 4 bytes long, every instruction. I don't know why. And to give you a headache, it has a second mode called, I forget the name, but there's a compressed mode. Remember, thumb mode, where everything is 2 bytes long. And I have no idea how that works. And if you do something like load an immediate 0 or load an immediate 1, the 0 and 1 are not apparently visible there. It's all somehow squished in. Anyway, and by the way, I can refer to a 4-byte address like this right here, and then have an opcode. So I don't understand that either. Somehow you cram 4 bytes of address and an opcode into 4 bytes here. So anyway, there are long tutorials explaining bit by bit what it all means, but it's not as simple as Intel. But if you refer to an immediate 32-bit value, you will just see that 32-bit value in 4 bytes sitting there. It's all squished into 4 bytes here. Anyway, there is technically no such thing as NOP in ARM. But there is a command that moves R0 into R0, thus accomplishing nothing. And that's what this is. This is the NOP. This is the command that moves the R0 into R0. That's what these zeros are, I think, although it's going to give you a headache. So this is something you could use for NOP. However, for our purposes, a NOP that contains null bytes is not worth anything because the null bytes will break our string. So we need a different kind of NOP. So what you can do is move R1 into R1. And what I expected to see is 0101, but instead you see 1001 for some mind-bending reason I have not gotten to the bottom of. But anyway, move 1 into 1 does give you a 4-byte NOP that doesn't have any zeros in it. So you can get a little further here. Anyway, so that's what's going on here. And this address here is the return address. After test PW, go to this address, 10524. So now we can put in a short password and see how it works. So if I continue, and I remember I'm looking for 10524. That's my expected return address. So I can continue here. And now I expect, oh, it has to continue again. Okay, there we are. Now it's going to ask me A. Okay, now I can examine the stack. And here it is, 10524. So it's exactly the same as before. Here's my A's. And in the 5th word after that is the return pointer. So now I know where the return pointer is. Now, I don't know what I'm going to do is inject a lot of junk and put my shellcode down here and just jump ahead. So I just picked a value down here somewhere to jump to after everything's over. And I'm planning to overwrite everything, put all the shellcode way down there. And that works to some extent. So that's my plan. Here's the A's I put in. There's the saved stack pointer. And I'm going to just write an exploit with dummy shellcode. So that's pw2a.py. Let me bring it up in my monitor, exit, and down and quit. And now down here, I can look at my exploit code with cat pwd2a.py, I think. Yep, good. All right. That is my exploit. It is not very big and it's not very complicated. And this, by the way, is the only one I'm able to get working very well today. So I have a prefix, which is A, B, C, and D. Then the next 4 bytes are going to go to the instruction pointer. I just made it point to another line, just a couple lines below. If you look up here, yeah, there you are. You can see it's going to, it's going to FC70 right there. So I just skipped a couple bytes and went right down there. So I'm just going to run the code that's down there which is, you know, not very far down. And now I just put in a bunch of NOPs. I put in 30 of these 4-byte NOPs, and then I put in a whole bunch of these things. Now this is as close as I can get to int3. int3 also does not exist on ARM, but this is called un. This is an unknown instruction. For some ungodly reason, there is an official thing called the unknown instruction, which causes it to break. So
What is it?
int3 is break in Intel. It causes you to stop execution, go back to the debugger. It's an interrupt signal. This is an unknown instruction which will cause a controlled crash, which amounts to the same thing for our purposes anyway. So now you print the prefix, the instruction pointer, the NOP sled, and then the buffer. And this way you can see if you have execution, because it should go through the NOPs and hit the unknown instruction. And if it's not able to execute, it will not process the NOPs. That was my plan. By the way, I should mention in passing that since everything is always 32 bits long, there are things in ARM that must be on aligned locations. You can't just move things forward 1, 2, or 3 bytes. There are things that must be on 16-bit boundaries. There are things that must be on 32-bit boundaries. So that can give you a headache eventually. Anyway, so there's my exploit. So I run that and put it in PWD2A, and now I can run the server, which will take that printed out data and serve it up for my remote debugger to have. So there it is, listening. So I go back up here and do this, and then I run this thing here again. Okay. All right, now I'm remotely debugging. Now I don't really need to delete the old breakpoints, it doesn't matter. I'm gonna have to specify the file, which is here. All right. And I don't care about that. All right, now I should be able to run and say yes. And it runs. And it paid it to start. Now I think I better put in that break at 9 because it won't have it because I left the debugger completely. Now I should be able to continue to the debugger. Now I hit the breakpoint. Now I should be able to examine the stack. Okay, so there's the A, B, C, D. Here's the address I jumped to. That's down here. This mess, E1, A0, 1001, is move R1 to R1. That's what passes for a NOP. So those are NOPs, and after a bunch of them, it will eventually hit something else. Let me look for a bigger portion of the stack here, like 50. Okay, and here you can see there's a whole bunch of those NOPs, and then you have this unknown instruction, FEDEFFE7, which will cause it to stop. So when I continue, it slides down and it hits the illegal instruction here, FCE0. It made it down to here. That's what you wanted to see. That's the illegal instruction. So it executed the NOPs. So now I have proven I can inject code and I can execute code on the stack. So I thought it would be smooth sailing from this point. Just use MSF Venom to make shellcode and run it. And it was not true at all. MSF Venom doesn't do it at all. Nobody does it at all. And I found out why. I spent the last couple of days digging through the internet trying to find some shellcode that works, and I can't find any that works because it is pretty hard to write good shellcode that works on ARM. So I found the most interesting tutorial where you practice a little bit of assembly here, which is kind of a good thing to do. But the end result is not shellcode that works. I have not found any shellcode that works anywhere yet, but there is some goofy exploit Python library that claims it can generate ARM shellcode, and I guess that's the next thing I'll try. I found a repository of like 20 shellcodes, but none of them work, and on it goes. But anyway, you can practice making your own shellcode, which is kind of good fun. So here, after getting that far, that I thought I'd write shellcode. So either way, you can prove that this, so I'm gonna make a listener. Okay, and here is raw shellcode in assembler, which I found someplace, and this actually runs, it just won't inject. So this is ARM, and then you go to thumb mode, and in thumb mode, you have only some of the instructions that are still valid, not all of them. But anyway, this mess sets a socket and a socket address, and it executes bin sh, and then it connects to this port number on the remote server, and that's the IP address of the remote server. So you can fill in the address of your GDB server and the port number here, 4444, and it will do a reverse shell calling back home. And the assembly code works. You have to compile it with AS and link it with LD with the -N for some reason. And then you can run it, and when you do, you will get a shell. So the raw assembler compiles to runnable code, and when you run it, it phones home. So that's good, clean fun. You can also stick it in C. You can generate it in binary. Object copy will take the runnable executable and take just the active ingredients and put it here. And then you can output with XXD. This will give you C code, which specifies the number of bytes, just the raw bytes in it, which is 80. So 80 bytes is all it takes to do a remote shell. And you can then put that in C. So you can use this stuff we've used before, where you put it in a variable called rshell bin, and then you just use this nonsense here to interpret the stored data as executable code and execute it. This is the same technique we used to sneak malware past antivirus engines in the past, and many tricks. You put binary data and then you execute it as if it was a function. So this will test your shellcode, and in fact, it works fine. You get a running shell. The problem is, you can probably spot it back here. There are a couple of problems. This is going to turn out to be the first problem. It has a line feed in it. Now the line feed is going to break the input because we're putting this into a password field. And it has null bytes in it. So this is pretty miserable shellcode. There's no way this is going to work. And of course it doesn't. When you try to put it in the exploit, you build the exploit like this. So you have the prefix and the instruction pointer to this. You have your NOP sled. Then you put in the shellcode. You print all that junk and run it. It's of course never going to work. And the reason it's not going to work is because you have 04, 1C, 0A, and after that, none of it goes forward. And you go back here, that was here, 1A, 04, 1C, 0A, then it's supposed to have an A1 and a 4A after that. And it doesn't get the A1 or the 4A or anything after that because the line feed terminates the password and all the rest of it is not passed up to the code. So you have to get rid of it. Now I had various brilliant ideas all day of how to fix this, and none of them worked. And there is no automatic thing like MSF Venom to do it for me, so I found so far. So I quit at this point. So this, like I said, this project is only half finished. This gets you to broken shellcode. Now, I had a lot of ideas, but so far none of them work. Yeah, so by next week, I imagine I'll have some shellcode that works, and maybe I'll talk about that. And maybe even a tool to make a lot of different shellcodes that work, like MSF Venom. I've also started with ARM64, and that was like really annoying. So I gave up on that and went back to this for a while. I might get ARM64 working by next week. But anyway, that's where we are. And I'm really glad to have this because this exploit development class originally only did 32-bit. Now I've added 64-bit, and I'd like to have ARM, 32, and 64. Those are all important. And I'd like to have all of them in this class as soon as possible. Yeah?
Should we try to do this project or wait till you fix the issue?
You can do it this way and get points. I put a flag in it. I'm just going to add to it. Okay. So I'll leave this. There'll just be later project coming. Go ahead and do it now if you like. And by the way, if you guys figure out how to improve it, that's worth extra credit, of course. There's a bunch of bugs in it, a bunch of defects. I'm sure you brilliant people can fix these problems and explain the parts I don't understand. I just threw it together like I always throw stuff together. I only halfway know what I'm doing. I'm sure some of you folks can do it. And if you do, let me know. Anyway, any questions about anything? See if any online people have anything. I haven't got any Kahoots or anything about this, but I might by next week. Let's see, here's some more questions. Okay, nothing. Okay, so I think I'm just gonna stop the recording and then I'll stop the share a little bit after that in case anybody wants to say anything.